Hi dears, now we are discussing with the topic waves in one dimension. In that topic we have already discussed the first topic, which is the one-dimensional wave equation. Now we can discuss the next topic, sinusoidal waves or solution to the wave equation. As we all know, in practically all the electric or magnetic generators are producing the electric and magnetic currents with the consequence of electric or magnetic fields which are varying sinusoidally with the time. That is why we are considering the sinusoidal wave and its solutions. So, we know that the sinusoidal wave in x direction can be written as f of xt is equal to a cos k into x minus vt plus delta, which is already familiar to us. And in this case, we all know A represents the amplitude of the wave, which represents the maximum displacement from the equilibrium position, and it is a positive quantity. Now delta. Delta is the initial phase or it is a phase constant. And also the argument of cos is known as phase. And when the initial time t is equal to 0, f of xt will be equal to a cos kx plus delta. When we look at these two equations, at t is equal to 0 means it is the initial time. At the initial time also there is a phase constant delta. That means the maximum will not be occurs at the origin or initial time. Now we can discuss this using this figure. That is, this equation which represents a sinusoidal wave traveling along positive x direction with a velocity v with a phase change delta can be represented using this given figure. In this figure, this is the amplitude of this wave, which is the maximum displacement, and this is the wavelength, and v is the velocity with which the wave is traveling along positive x direction. Now we know that the wave, in this case, the wave will not be having its maximum value at the origin, even though at t is equal to 0. So, we simply consider the central maximum at a particular point before the origin. Now, we can prove that. Consider f of xt is equal to a cos into kx minus vt plus delta. In this displacement, this equation represents the displacement of this plane. This can be maximum only when the cosine term is having maximum value, as the amplitude is already a positive quantity. So, we are just taking outside the k value, k into x minus vt plus delta by k. And we know the maximum value for cosine is equal to 1 and the angle is equal to 0. So, the angle is x minus vt plus delta by k, which is also equal to 0. That is, x is equal to vt minus delta by k. At any time t, for a wave traveling with a velocity v, x will be equal to vt minus delta by k, where x is representing the central maximum. And also, when t is equal to 0, when t is equal to 0, from this equation we can write x is equal to minus delta by k. X is equal to minus delta by k. Look at this figure. This is the displacement difference with the central maximum and the origin. That is, at t is equal to 0, the central maximum is just before the origin by a term minus delta by k. So, this difference is minus delta by k, or simply delta by k along negative direction. That is, the central maximum is delayed by a term minus delta by k from its origin. That is, the displacement maximum is delayed by a term delta by k at the origin. Now we can consider one more special case. That is, if there is no phase lag, we can say delta will be equal to 0. As we know, x is equal to vt minus delta by k and delta is 0. We can write it as x is equal consider the case when t is equal to 0, this x also will be equal to 0. That is, in such a case where the phase lag is 0 and it is at the time t is equal to 0, the central maximum will be at the origin. That is, looks like this. This will be the central maximum. The terms which we use along this derivation are: v is the velocity of the wave, k is the wave number, lambda is the wavelength of the wave, t is the period of one cycle, and nu is the frequency, and omega is the angular frequency, and delta is the phase constant. One more thing about the phase constant delta. If we add any integer multiple of 2 pi with this phase constant, the f of xt will be invariant. That is, if we add any integer multiple of 2 pi to this delta, these equations will be invariant and not effective. Now, we can consider the solution will be representing the wave equation. Dou square f by dou square is equal to 1 by v square dou square f by dou t square. And the relation between the wave number and lambda, we already know k is equal to 2 pi by lambda, or lambda is equal to 2 pi by k. Now, when the wave completes 2 pi by k distances, or it traverses a distance of 2 pi by k, it completes at one period of cycle. When it traverses through the right direction or positive x direction with a velocity v, we can consider the period of one cycle t is equal to lambda by v, and that can be written as 2 pi by k divided by v. And also the frequency of wave nu can be obtained as the reciprocal of the period, that is 1 by t, which is equal to kv by 2. And also we know lambda is equal to 2 pi by k, then already I have substituted 2 pi by k or k by 2 pi as 1 by lambda. Frequency is the number of oscillation per unit time, which is we obtained as v by lambda. Now we know the angular frequency omega, which is same quantity which we consider in the uniform circular motion, which is the area swept out per unit time. Angular frequency omega is equal to 2 pi nu, that is 2 pi into kv by 2 pi, which is equal to k. Now we can substitute this omega instead of kv in the wave solution. As we know, f of xt is equal to a cos k into x minus vt plus delta. I have taken the k inside this bracket. That is kx minus kvt plus delta. Now we can substitute this kv as omega. That is f of xt is equal to a into cos kx minus omega t plus delta. This is the sinusoidal wave solution. If dou square f by dou x square is equal to 1 by v square dou square f by dou t square represent a sinusoidal wave in one dimension, then the solution will be f of xt is equal to a cos kx minus omega t plus delta for a wave which is varying sinusoidally with respect to time along the positive x direction. Now we can consider the same solution of wave equation when the wave is traveling along the negative x direction. That is, in this figure the wave is traveling along this direction with a velocity v. In this case also, the central maximum will not be having at the origin at any instant. It occurs only in the special cases. So, I am going to consider this equation as f of xt is equal to a cos minus of kx, since the x component is negative, minus of kx minus omega t plus delta, which represent the same wave with the wave will be having a property of same amplitude, phase constant, velocity and angular frequency which is traveling in the opposite direction. Now we can replace this equation. F of xt is equal to a cos, taking the negative sign outside from bracket, kx plus omega t minus of delta. And we know the cosine function is an even function. We can neglect this negative sign, thus cos minus theta is equal to cos theta itself. So A cos kx plus omega t minus delta. That is, this is the solution which is representing the wave traveling in the positive x direction, and this is the solution when the wave is traveling in the negative x direction. Simply, we can switch this equation by substituting a negative value to the k. So, in this case, the central maximum will be delayed to the right side by the same quantity delta by k. That is, this is the delay with the central maximum and the origin as the wave is traveling along the negative x direction.